Hello, we have developed a new method for learning tasks on neural fields. Most ways of representing 2D and 3D data are discrete. They assign values to a finite set of points. Recently, neural fields emerged as a way to represent data continuously. It's a small, multi-layer perceptron that learns to map every point in space to its corresponding value. Neural fields are great at capturing high-dimensional and high-frequency data. But whereas we have powerful architectures for learning on discrete data, we don't really know how to do learning on neural fields. We need some way of choosing which points on the field to evaluate for downstream tasks. We call these points a discretization of the field. Certain discretizations are better than others. If we're trying to classify an image, discretizing the domain badly can lead to the wrong predictions. But it's difficult to know how to discretize your domain in an optimal way for each task. The best we can do a priori is to limit how much a model's predictions can vary when presented with different discretizations of the same neural field. Numerical integration gives a natural upper bound on this kind of discretization error. The difference between the integral and the sample mean of a function is bounded by its variation, which is how much the function fluctuates over its domain, and the discrepancy of the discretization, which is how well the points cover the domain. So how do we design a neural network that can be described by such an upper bound? We specify a discretization invariance layer as the integral of some parametric map that takes a neural field as input. The layer computes the sample mean of this map with respect to a given discretization. A discretization invariance layer can be vector valued or neural field valued, the latter meaning that the output is well defined on the same domain as the input. By composing discretization invariance layers with nonlinearities, we can obtain a discretization invariance network, which we call DINet. DINet encapsulates a large family of networks that include neural operators and continuous convolutional networks. This gives us a simple way to extend discrete networks like CNNs by replacing discrete convolutions and pooling layers with continuous discretization invariance versions. The resulting convolutional DINets can combine all the techniques of standard CNNs as well as techniques from continuous convolutions like kernels defined by multilayer perceptrons. We apply DINet to a wide range of tasks, including ImageNet classification, cityscape segmentation, and prediction of signed distance functions. We find that DINet often generalizes to new types of input resolutions and discretization schemes at test time, and can also be trained and tested on different types of neural fields. Please check out our poster and code for more information.